Hey everyone, welcome to this explainer. Okay, today we're diving into something that trips up a lot of people, completely dead laptop motherboards. But don't worry, I'm going to be acting as your senior repair mentor today. We'll be unlocking some of those closely guarded professional secrets so you can confidently tackle even the most complex hardware issues. We're going to take what usually looks like a chaotic maze of circuitry and turn it into a highly logical, easily navigable map. So, grab your multimeters, get comfortable, and let's jump right in.
Assalamu alaikum, meet Ismail, an absolute technology genius.
He'll take you from basic electrical theory straight into real, hands-on builds.
Hit subscribe for weekly explainers and let's start building today.
To do this, we're following a three-part troubleshooting roadmap today. First up, we'll look at the live power sequence. Then we'll cover the unpowered continuity secret. And finally, we'll wrap up by mapping B+ on schematics. All right, let's start with phase one, the live power sequence. This is all about measuring live voltages right there on the physical board. Now, before you even think about touching a live board, we have to talk safety. These are non-negotiable. Step one, wear your anti-static wrist strap. Seriously, never skip this. You do not want to fry the components you're trying to fix. Step two, anchor the black probe of your multimeter to a solid ground. A metal chassis or the negative terminal of a capacitor works perfectly to give you an accurate baseline. And step three, set your multimeter to exactly 20 volts. Why? Because we want to cleanly capture that primary 19-volt input without blowing out our meter. Okay, so look at this. Knowing your healthy baselines versus your failed readings is literally your best diagnostic weapon. If you've got a healthy board, you're going to see a rock-solid 19 volts at the DC jack and the charge IC inductor. And over at the battery charging pins, you should see 3.3 volts. Now, if you probe those exact points and get a dead zero, or maybe the numbers are just wildly fluctuating, well, boom, you instantly know where the failure is. Comparing these healthy baselines against failed readings makes your whole diagnostic process so much more efficient. As we're physically tracing that 19-volt path to find our secondary 3.3-volt and 5-volt rails, it really helps to remember what these little components are actually doing. Capacitors, think of them as your noise filters. They're constantly cleaning up electrical noise from that main power rail. Inductors, on the other hand, are the stabilizers. They make sure the current flow stays perfectly steady. When they work together, they keep your power rails robust and totally reliable. You know, a question I get asked all the time here is, hey, if my main 19-volt rail is testing perfectly fine, why on earth do I still need to check the battery connector pins? Well, think about it like this. A charge circuit can have a partial failure. The board is successfully receiving the 19 volts, sure, but it's completely failed to generate that specific 3.3-volt signal that actually tells the battery to charge. It's exactly like having a guest standing right at your front door, but they just aren't knocking. They are physically there, but absolutely nothing is happening. So remember, confirming the main voltage is never enough. You always got to verify the signal too. Moving right along to phase two, the unpowered continuity secret. This is how we trace circuits safely with absolutely zero risk. It's simple, really. Zero voltage means zero risk. By completely unplugging the power adapter and dropping the board's voltage to absolute zero, we completely eliminate that terrifying risk of accidentally shorting out sensitive components with our probes. Instead, we can safely verify the structural circuit map. We're proving the pathways actually exist without the anxiety of live electricity coursing through the system. All right, so here's the exact unpowered procedure that usually only top-level experts use. First, set your multimeter to the buzzer or continuity function. Step one, anchor one probe securely onto that main 19-volt inductor. Just leave it right there. Step two, take your second probe and touch it to the various secondary inductors scattered all across the board. And step three, listen closely. When you hear that satisfying little continuity beep, or you see a very low resistance reading pop up on your screen, you've got definitive proof. That beep means the circuit is perfectly connected. It physically proves that the main voltage path is successfully reaching those distant secondary circuits without any structural blockages. It is honestly such an amazing trick to check rail integrity without plugging a single thing in. Okay, let's wrap this up with phase three, mapping B+ on schematics. This is where we translate those physical tests directly to standard engineering diagrams. The very first thing you do when you open up one of those massive, intimidating schematic diagrams, you go hunting for the B+ or VIN mark. This symbol is crucial. It indicates the primary 19-volt input power rail, basically the main distributor sending voltage to all the different sections of the motherboard. Spotting these marks is always your very first step on any schematic troubleshooting journey. And when you trace this B+ connection, you reveal this huge distribution path. We're talking vital subcircuits here. The 3-volt and 5-volt always-on circuit, the 1.5-volt memory circuit, and of course, the absolutely critical CPU core power. All of these must receive that main B+ voltage before they can even attempt to do their specific jobs. When you trace this connection on the schematic, it dramatically simplifies your whole diagnostic process because you can clearly see exactly who relies on that main power feed. Think of it this way. On both the schematics and the physical board itself, these input inductors act as literal doors or gateways. Mapping these 19-volt input inductors shows you exactly where you need to place your multimeter probes right before the power steps down to lower voltages. Having this visual guide completely changes how you look at the hardware. Suddenly, a chaotic, complex motherboard is just an open book. You know exactly where the power enters and exactly which doors it has to pass through. So, as you can see, this professional diagnostic checklist really does turn a totally dead, complicated board into an easy-to-read map. We've successfully used isolated power rail checks and unpowered continuity testing to navigate it perfectly. But, this leaves us with one final, exciting thought. If we can solve this many problems just by checking isolated power rails, what other deep secrets are hidden inside these schematics? What other invisible pathways and clever tricks are just waiting in there to make an impossible repair totally possible? Keep fueling that curiosity, keep tracing those invisible paths, and hey, thank you so much for joining me on this explainer.